So good afternoon, everyone, and special thanks to the organizers, Yasir, Subhro, and all the others. I mean, ICTS is a lovely place. Those who have not been able to come here physically must come just to see these flowers. I mean, every time I visit ICTS, I never fail to be captivated by these beautiful lotuses and so many other things in the campus. So let me start my talk. In the next 40 odd minutes, I'll speak about a theory that we developed to describe the physics of a material, real material, which it turns out is a hexamerized quantum paramagnet, and of course it exhibits magnetization plateaus. I can put this here. Yeah. So my collaborators in this work are my former student, Meghdeepa, who is in the audience. Now she's a postdoc with Yasir, and Arno Ralko, my old-time friend from, during my postdoc days, we shared the office. He's in Nell Institute. And this is a work published later last year, funded by SERB. So this work is basically a study of this material, theoretical investigation of the properties exhibited by this material. It's a distorted honeycomb of spin halves. So the blue dots here are the copper ions connected via this these organic ligands. PYMCA, I guess, means pyrimidine carboxylate or something. Excuse my sort of ignorance about the details of PYMCA. But the key point is there are copper ions, which are effectively spin halves sitting at forming this honeycomb lattice. And this lattice is distorted in the sense that although honeycomb is of course a very simple lattice, but there is a slight variation on that lattice that this material exhibits. And that variation is that the bond lengths are not all equal. So it's a distorted honeycomb. And this actually, if you notice carefully, so although of course basic honeycomb is has a unit cell with 2 lattice points per unit cell, in this case it has 6 atoms per unit cell. So it's an effectively, I mean, it's a hexamerized honeycomb lattice because it has 3 unequal bonds. And the other notable point about this, the arrangement, the superstructure that these pink and cyan and yellow color bonds make is that they form a Kagome superstructure. So just to sort of connect that fact easily, I have just read on it a little more carefully. So if you just focus on the red bonds, they form Kagome superstructure. So why is it not going forward? And so, we sort of like to call it a Kagome-Honeycomb lattice. It's not a Kagome lattice, but it's a honeycomb lattice where the bond lengths form a superstructure which is Kagome type. And these distortions that this honeycomb material exhibits are, in fact, there was a theorem there was a theorem by Lieb and Frank with motivations from graphene that what sort of lattice distortion may be allowed on a graphene structure. And this was one of the most likely type structures according to them. And it's just a coincidence that I noticed that paper and I realized that this material actually is consistent with what the theorem seems to suggest about the possible distortions. But that is not the main point. The main point is that this material exhibits quantum paramagnetic behavior, which basically means it stays non-magnetic down to lowest temperatures at which the measurements have been done. And also it exhibits magnetization plateaus as a function of field when you apply the external field. So for instance, the susceptibility is pretty smooth. Yes? It is, well, so the usual thermal paramagnet is paramagnetic because of thermal fluctuations, the high temperature phase. So all sufficiently high temperature phases are the same kind of thermal paramagnets with zero magnetic moment because of thermal fluctuations. Here, if you lower the temperature, as this is what the next, then there is no signal of any ordering transition. It just smoothly, the susceptibility just smoothly going to zero, as if there is a gap opening up and there is no magnetic moment ever developing. So while the temperature fluctuations have been considerably reduced, this is already at, I think the lowest temperature they reached for 2 or 1 Kelvin, and there is no sign of any ordering. Even the specific heat exhibits a very smooth behavior, no cusps, no signatures of any ordering transition. So no magnetic moment ever develops, even if you have sort of gone to sufficiently low temperature. So that is what is quantum about this paramagnet. So it's not a paramagnet because there are thermal fluctuation. It's a paramagnetic because of the quantum mechanical, the nature of the quantum mechanical nature of the spins and the interactions between them. So, yeah, it's a spin gap non-magnetic system. And that is what, so if you find the term quantum paramagnetic little too remote, then just remember that it's a spin gap system, which is also non-magnetic. So it never exhibits. So there is some quantum mechanical state that the system is actually going into as you lower the temperature, which is being protected by some sort of gap, and it never exhibits any non-trivial magnetic ordering. In fact, no magnetic ordering. In addition, the other notable feature of this, yeah.
Is that specific heat also exponential?
Well, there is no detailed specific heat analysis as such presented in the paper, but they do remark that there is no signature of any transition in the specific heat.
No, but this.
Yeah, I know it looks that is the first impression, but I should ask the experimentalists whether they have subtracted off the other parts, the T cube and so on. So just on the face of it, it could even look T cube. I don't know, but yeah. But yes, the experimental paper claims, and there is a further report more recently affirming this susceptibility behavior, that this system is a gapped system with no signatures of any ordering transition. So if there was an ordering transition, specific heat should exhibit some cusp, some signature of that, which it doesn't, down to these relevant temperatures. You can also see I had maybe there was just 1 second. Somehow the movement of slides is a bit slow. There was anyway, let me go ahead. So for instance, the Q-revised temperature measured from high temperature susceptibility is of the order of some 40 odd Kelvin with a negative sign, which means there is a strong enough antiferromagnetic exchange overall present in the system, and yet it's a non-magnetic system with a gap. The other important feature that this material exhibits is magnetization plateaus. So as you can see, when you apply magnetic field, and these are at the temperatures are shown here, there is a sort of nearly flat. Of course, this is not a flat thing, but let's say nearly very slowly. So initially the rise in the magnetization is very slow, but then there are these rapid rises, and then again it slows down, then again rises. It's very much basically like the plateaus that you typically experimentally observe if there were plateaus. And so this is a clear signature that the system exhibits magnetization plateaus. And these magnetization plateaus are not at some random fractional values, but fractional in terms of saturation magnetization, but at 1/3 and 2/3. There is also a small plateauing tendency here, but we don't sort of quite understand it. So let us say there are two clear plateaus, one very clear, prominent, which is 1/3 plateau, and the other one which is somewhat weak, but still there is an indication there is a plateau that occurs there at 2/3. So these sort of, so the Curie-wise temperature is about 50 Kelvin with a minus sign, which basically means it's antiferromagnetic. So there is sufficiently, so it's a antiferromagnetic spin system with strong enough, not very strong like 1000 Kelvins, but let us say 50 odd Kelvin antiferromagnetic strength. And down to 1 or 2 Kelvins, it showed no signs of any magnetic transition, and it does show magnetization plateaus at 1 or 2. So the question is, the interesting thing about this material at the simplistic level, one can always add on more and more pieces of puzzles to any story, but we want to keep things simple and ask, look, this material it forms a structure which is actually unfrustrated. A honeycomb is a bipartite network. So if you have spins sitting on honeycomb lattice and interacting via antiferromagnetic exchange, then generally you would expect them to order. And there is no magnetic order here. So the question is, of course, there is an additional element here, which is that the honeycomb is not perfect, but very slightly distorted, so as to form this sort of Kagome superstructure of couplings. So the question is, what kind of non-magnetic phase this material goes into, and why there are these two specific plateaus that it exhibits, given this basic motif, which is this Kagome-Honeycomb structure that these spin half ions are forming. So that is our motivation, and this is basically the work that we present here. So the basic model is already quite clear in everybody's mind. We have a spin half on this lattice, which basically just redrawn for our purpose in calculation. So this is a honeycomb lattice with red, green and blue bonds, and the exchange interactions on them are 3 numbers, JA, JB, JC, and all of them are antiferromagnetic. So this is our basic model for this material. Just to fill in some more details, so the Hamiltonian of this system is sum over these 3 types of interactions, A, B, and C. And there is another way in which you can, it will turn out to be useful to think of this material as a system of coupled hexagons. So if you focus on any one of these there are 3 types of hexagons here if you notice carefully. So let me help you out. So think about red, green, red, green, red, green hexagon. That is your AB hexagon. And then you can clearly see that these AB hexagons are all connected by blue bonds, the third coupling. So you can actually think of this material or this model as a collection of hexagons coupled via antiferromagnetic. In fact, it turns out this is not the first time such a geometry is sort of playing or sort of arising in a material and prompting us to make some investigation. One of the earliest material that has been known for the Kagome antiferromagnets is actually a material relies on the same geometry. So this material, again, some organic name which I can't really, I don't know the full form, but anyway, this is some organic salt which actually forms a same sort of Kagome-Honeycomb pattern, in which the antiferromagnetic hexagons were coupled by ferromagnetic coupling. So the material that I'm presently investigating is where all couplings are antiferromagnetic. But suppose if you made the blue bonds all ferromagnetic and strong, this problem effectively turns into, or let us say all the red bonds ferromagnetic and strong, this problem would effectively turn into a spin 1 Kagome antiferromagnet. And we have also done some work on that in the past. So,
Brijesh?
Yes?
So this is Yogesh. So
yes, boliye Yogesh. Yes, please.
In this spin 1 Kagome, what is the magnetic entity?
Well, magnetic entity is not a single copper-like ion, but this collective organic complex which seems to have an effective spin half.
I see.
Yeah.
I see.
So
Okay,
there is
thanks.
no, yeah, that is the, Yes.
Okay. Thank
You can
you.
look at this paper by, this was the first paper, and then.
Sure. Thank you.
So this is the basic model that you would like as a theorist to start answering the questions that I posed in the beginning of my talk. What kind of non-magnetic gap phase this system is going into, if at all, which is what the experiment seemed to suggest, and why there are these two plateaus that seem to arise in this material. So this is just to sort of choose some convenient calculational units. So my A plus B plus C is 1. And now let me think about some limiting cases. In fact, it's always good to think of limiting cases first and then build a theory around them. And let us see if those limiting cases have some element of truth in them. So one simple limiting case of this model problem is, imagine JC is 1, which means JB and JA are 0, for instance. So all these, so why is it going? Maybe I pressed the wrong button. Yeah. So if your blue bonds are all the strongest ones and others are, let us say, ideally 0, then this is just a collection of independent dimers, which means a pair of spin halves interacting antiferromagnetically, and there are plenty of them forming this lattice. Then naturally the ground state is a direct product of singlet on each of these blue bonds. So let us call it dimer singlet. It is something that has been, there are different contexts in which dimer singlet phases arise. And this is obviously a gap phase, because breaking a singlet would require an energy of order JC. And it's quantum paramagnetic. This is the most trivial example of quantum paramagnet, if anybody wants to remember, because it has no magnetic moment, but not because of thermal fluctuations. There are no thermal fluctuations. We are talking about ground state. But because quantum mechanical fluctuations pair up, down with down, up, and form an entangled quantum state, which in totality never exhibits any magnetic moment. So it's a quantum paramagnet of the simplest type, just collection of dimers, singlets. The other limiting case of this model problem is where you imagine that JC is 0. So I told you the other perspective to think of this material or model is that there are hexagons connected via this antiferromagnetic coupling JC. So if JC is 0, then you are only left with a collection of independent AB hexagons. And again, these are antiferromagnetic hexagons. And we know you can solve this problem. It's more difficult than solving the Heisenberg problem for a single dimer, but you can easily do it. And again, the ground state is a singlet. But now it's not a singlet of a pair of spins. It's a singlet made by these 6 spin halves, which are forming this motif, the hexagon. So let us call this as the hexagonal singlet or a hexamer state. So dimer state, dimer singlet is the one which is formed by a pair of spin half, and a hexamer singlet is a state formed by the 6 spins forming this AB hexagon. So these are two, and this is also going to be gapped, and this is also a quantum paramagnet. So these are two very likely states the system may be going into when it shows no signs of ordering and shows gap-like behavior, smooth suppression of susceptibility as you lower the temperature. So let us see if any of these two states are good candidates which capture the physics of this material. And of course, one other limiting case is the uniform honeycomb, which, as I said, there is no surprise. It has to order, and it orders, and it exhibits this up-down kind of arrangement. Yes. That's. So now let us discuss the phase diagram. Somehow this is, the transition is slow, but never. So we will discuss the phase diagram in this so-called ternary space. It's just convenient to think of it, so it's basically satisfying this constraint A plus B plus C equal to 1. So in this phase diagram or phase space, the centroid is the uniform honeycomb. The three corners represent three idealized type of dimer states, either A dimers being independent, or B dimers, or C dimers. And the three sides of the triangle are the ideal AB or AC or BC hexagons. And as you move into this triangular region, so these are just the corners and the sides, as you move into, so on this side you can say, okay, I had hexagonal state, now I'm moving in. So let us ask a question for how long this hexagonal singlet state would survive before eventually falling into an ordered state, because we know at center it must reach an ordered state. So exactly where does it reach that order, we don't know, but we have to investigate that. But we are sure that on the sides, so approaching the centroid from the sides, you would see the regions of stability of hexagonal state if you can do a systematic calculation, and eventually a region in which the order will arise. So we did sort of calculations by two different methods. One is basically a triplon analysis approach. It's an stability analysis for any quantum, I mean these simplistic quantum paramagnetic states like dimers, or in this case hexamer. So we know in the limiting case the hexamer state, let us say, is a ground state. So now if we turn on the couplings, well, turning on the coupling by a small amount isn't going to kill it completely, but it is going to make it sort of fluctuate from the singlet to the nearest triplets. So we restrict our sort of description at a low energy level to the fluctuations to the triplet level, and develop a theory. This is triplon analysis, and hence the term triplon. So these are basically describing triplon fluctuations with reference to the chosen singlet state, in this case the hexamer. So we can do it with respect to dimer singlets or with respect to hexamer, both are possible. Let me not go into technical details to sort of, people interested can discuss with me or look at the paper. But let me just discuss the phase diagram as we obtained from the triplon analysis, the stability analysis of these candidate quantum paramagnetic states. So what we find that this hexamer singlet phase, and these three are equivalent regions because of the symmetry between A, B, and C bonds. So you can just focus on any one of them. So let us focus on AB hexagons coupled via C coupling. So you obviously expect AB hexamer singlet state, and then it continues for actually quite a large portion of this triangle until it hits this black boundary, and that is where the gap continuously closes. So this is in fact the calculation of gap from this triplon analysis. So you can, so this black line here, this black continuous line here of the central region is the boundary obtained from triplon analysis by following the gap, and the gap continuously closes at this point. So there is, and the closing of a gap in triplon analysis is a mark of ordering transition. So this in fact exhibits a transition from, this theory tells you two things, that in what region of the phase space the hexamer state is stable, and eventually what sort of ordering instability does it exhibit, and it exhibits an instability towards nil order. So this is the two pieces. So this is what it tells you, and you can do it from either side, you get the same answer. So it's there is a symmetry, sort of threefold symmetry here. Then you, as I said, dimers are also candidate states. Instead of starting from this baseline, if you had started from this corner, which is the C dimers being independent, then you can also do triplon analysis and ask in what region the dimer is stable. And what we find is that only in this tiny region between these two dashed blue lines that the dimer phase is stable. So, and eventually again it goes into the nil ordered state. So this is the phase diagram. The phase diagram is actually dominated by hexamer singlet state, and only in a tiny region in the center, around the centroid, of course, there is an L order. And there are also, whenever the two kinds of hexamer states compete in this sort of frustrating interfacial region, the dimer phase ends up winning. So for instance, whether to form AC hexagon or to form AB hexagon, well, it ends up forming neither but a dimer state. Okay, so that is what these little bluish regions, I mean, the regions with bluish boundaries, blue boundaries are.
The question.
Yes.
Sorry, I have a question.
Yes, please.
Actually, maybe even two. So, when you talk about triplon, what do you precisely mean? I mean, what is your starting point?
Yes. Can I use both?
Certainly, yes. I mean, I don't mind.
So, suppose you have a pair of spins, spin halves. Okay. Now, this pair of spin half interacted via interaction J, and you have very nicely described all of this in the tutorial. So what does it form? It forms 3 states, minus 3j by 4, j by 4. This is your singlet, and these are your 3 triplets. Call them T1, T0, T1 bar. And there is a gap. This is ideal picture. Now, same thing you can do for hexagon. So your ground state is some hexamer singlet. In fact, that is what the energy level diagram was. I can even show earlier. I skipped it just to avoid. So this is in fact the energy level diagram of a single hexagon. So I'm starting from the limiting case and then building a low energy theory. So what is the limit? Limit is independent hexagons. What are the eigenstates of those? This black line is the unique singlet state which the hexagon would realize. And then there is a lowest, well, next to that is a triplet. And there are 2 more degenerate triplets. This blue dashed line is also a triplet. Okay, so the low energy Hilbert space that we consider. So first thing, what is your triplon? The triplon is an excitation so let's say your reference state is singlet and the excitations are triplets. And these excitations dispersing on a lattice mediated by the couplings between them are called triplons. So the effective theory is built in this space. And this is a 10-dimensional Hilbert space, but the singlet is treated as an average number. So there is a given average singlet background. So essentially you have 9 triplet of, 3 triplets, so total 9 triplons if you wish.
Right. I mean, the reason I ask, because triplons are usually related to the excitations of a singlet bond.
No, singlet bond.
I understand you mean triplet excitations of a hexagon that are propagating. Do you do like a perturbation expansion? Or
no,
do you
due to the
wave expansion.
Due to the exchange interactions between these connectors.
So this is the first order perturbation theory for the hopping of the.
I wouldn't say it's perturbation theory, because if you think about dispersion, the dispersion would have contributions coming from. Yeah.
Okay, we can.
We will discuss that. Okay. Phase diagram, yes. But this is what I mean by triplon here. So I'm using the term triplon just for everybody's. Yeah.
Yep.
Okay. These dashed lines, you mean black dashed lines? Well, this is basic. So suppose you. Okay. This dashed line just means, what do they mean? Okay, so if you calculate the dimer energy and you calculate the hexamer energy and you compare them, then the hexamer energy is lower in this region, which is partly blue dotted line and partly dashed line. Which means across the dashed line, there is no dimer at all. There is a directly, either it is AB or AC hexagon. Sorry, say it again. Even if my. Well, this region, if you do more careful calculation, it would more likely a very highly suppressed little line. So in this most basic calculation, it seems to not just be there. So it's like an exponentially tiny region funnels out and forms. And by the way, this has been corroborated recently by another set of people following up our work. So indeed, there is a dimer phase between these two hexamer phases. But if you were to sort of, so at the level of our calculations, this is just the region from which AB hexagons become AC hexagons. So, well, this red little lines just mean that, okay, you could in principle just forget about dimer calculation and just get this triangular region directly from the hexamer analysis. I mean the triplon analysis of the hexamer background. That would also have given you the same region, but it would be slightly different in those areas where I have shown it by red little patches. And that is energetically less favorable. The direct transition is happening from dimer to the null order. So in these, right, so I'm doing a patchwork here. I'm taking a few different reference states and trying to approach the null phase. And I'm saying in this region, the null phase is approached directly from the hexamer side. But along these dashed lines and this region between the blue dashed lines, this is the dimer phase, and the transition is happening from the dimer to the null phase. That's right, that's right. So in this region here, the dimer is the winner. Yeah. And one more way to think about this, why this region shrinks or ideally is not there even if the coupling is strong, because you see, this entire line is sort of frustrated as far as, suppose this is AC or BC. So whether the C partners with A or C partners with B. So it always prefers to, I mean, it remains confused most of the time, but eventually only in this region it ends up forming a clear dimer phase. Or in other words, AC hexagon itself is a dimerized hexagon. So whatever propensities for dimerization there are, they don't have to be separately existing. They are anyway part of the hexamer state. So it's a sort of tricky region that arises. But it is there for sure, and it has been corroborated further by other people recently. So yeah, I have sort of explained most of this. And then this is further supported by unbiased numerical simulations done by Arno and Megadipa. And so these yellow sort of discs, pale colored discs, are the intensity of the strength of stiffness. So stiffness is a measure of how sort of rigid is the order. Which means it's a measure of the stability of the null order. In this case, it's the null order only. So you compute stiffness and you find that it is very stiff or very good, strong order, and then eventually the stiffness nearly vanishes around this analytical boundary or the triplon theory boundary, and eventually it is zero everywhere. So it's and this agreement is actually quite good. I mean, I'll show you this line. So just imagine traversing along this line. So starting from AB hexagon and going towards this corner. So you start from AB hexagons, you get no stiffness or no order parameter. These are the two quantities computed from QMC. And the transition point here is nearly, I mean, they are basically same. On this side, the dimer phase versus null phase transition, our analysis sort of is slightly overestimating the singlet phase, whereas the numerics is, but still it is on the same scale. This is 0.4 versus 0.44 or something. So the agreement between theory and numerics is quite good. And as I said, this is the paper I was mentioning. This is a very recent paper where they do find all the basic elements of this phase diagram. So let us now quickly discuss the magnetization behavior. Okay, so you apply a magnetic field, and again, the phase diagram is dominated by hexamer phase. So let us sort of just focus on the magnetization problem, effective problem with reference to the hexamer state. So let us look at the energy level crossings as a function of field for a single hexamer. and see what degree of truth there is, if at all of any relevance to the experimentally seen magnetization behavior. And the answer is, it pretty much has all that experiments are showing, but in a heavily renormalized manner. So if you see, the ground state is singlet, and it survives up to some field, then it goes into the next triplet, which is rapidly coming down. The M by M saturation is 1/3 here. Then it goes into the 2/3 state, and eventually it saturates. So even at the isolated hexagon level, the qualitatives of what the experiments seem to find, the non-magnetic state, then slow rise, and then plateauing out at 2/3, then again a rise, and then again plateauing at, 1/3 and then 2/3. That element experimental observation is already present at the isolated hexagon level. So now we sort of go beyond it and do this stability analysis, that if this were my reference state, or if this were my reference state, it's like doing the stability analysis of these three. I mean, this we have already done. So these two plateau regions will give you the boundaries of the plateaus, and then we compare it with the numerics and so on. So, so yeah, this is what I was saying, that what we see in experiment is already qualitatively present at the hexamer level, which is already in turn saying that the physics of this material is indeed dominated by or governed by the hexamer phase and not any other thing. So let us quickly do the analysis. And yes, so what? So this is an interesting. So this is the same phase diagram, but now what we have done is imposed on it the magnetic piece of information. So what is that? So this orange color region with this orange boundary is the region in which. So this phase diagram is like set of samples. So if your sample was here, or if it was here, if it lies in the orange region, as a function of field, it would exhibit 1/3 plateau. If it lied in white region, as a function of field, it would not exhibit 1/3 plateau. And this purple line says that within this orange region, if your sample lied between the baseline and the purple line, then it would also exhibit 2/3 plateau. And between the orange line and the purple line, it would only exhibit 1/3 plateau. So what this phase diagram is telling, so imagine there is a field axis coming out of the plane of this phase diagram. Then depending upon where you are in this orange region, you would either see 1/3 plateau, or you would see 1/3 and 2/3 plateaus. And if you are outside the orange region, you would see no plateaus. So this is your magnetic phase diagram. And the other notable point is that this so-called plateau physics is strictly lying in the hexagonal region. Means those phases, those parts of the phase diagram where the hexamer singlet phase is realized, which means the occurrence of 1/3 plateau is in fact telling you in converse that the ground state of this material in the absence of field very much must be a hexamer singlet, because otherwise it would not show these two plateaus, at least within this basic simple model. And this is just a comparison of this. So as I said, the analysis, stability analysis of plateaus in the same spirit as we did the Triplon analysis would give you the boundaries. That is how we generate these boundaries. And the numerics, this continue, I mean this line, the blue line is QMC numerics, and the phase boundaries are, the plateau boundaries are pretty much in good agreement. And it also clearly exhibits. So for instance, here if you look at this bunch of lines, the blue line shows two plateaus, but as you increase JC, so you are sort of coming from this side. This is 0 JC, and this line is going towards JC1. So as you increase JC, you basically lose, at first you lose 2/3 plateau, and then eventually you also lose 1/3 plateau. So this is absolutely consistent with the numerics. The basic sort of theoretical understanding is consistent with what the unbiased numerics tells us. So what do we obtain? We obtain 2 plateaus, or 1 plateaus, or no plateaus, which is what the basic idea, basic outcome of these calculations is, and depicted in this phase diagram. And the key point is magnetization plateaus occur only in the hexagonal singlet phase, which means the susceptibility, specific heat measurements indicating a non-magnetic gap behavior, combined with the existence of magnetization plateau diagram, I mean the two magnetization plateaus, completely sort of fixes the physics of this material. It is saying that this material indeed realizes a hexamer singlet phase in the absence of field. Yeah, this is what I had been saying. And the other point that, okay, we also estimated the couplings, JABC. So basically, let me show, I think, yeah, this is. So I just requested experimental people to share their data with us, and then we sort of played with our calculations and tried to see which is the closest to this. And these are our estimates, which are also in somewhat the same, I mean, the numbers are nearly same as the experimental people suggest, and the subsequent paper also estimated them, except that their JC is slightly stronger than ours. Ours is equal. So this is really a system which is a collection of hexamers or hexagons at the model level. So JC is very weak, compared 6 times weaker compared to JA and JB. JA and JB are pretty much same, although they can also be slightly different, but they will still give the same physics. Yeah, these little black lines here just indicate the positions of the positions of this material here. One notable point about this estimation is that this material lies very close to the purple boundary, which actually is interesting. This is a material which is sort of, the ligands are organic molecules, and they can easily be sort of, unlike inorganic systems which are much harder, systems with organic entities, they can be compressed or, manipulated a little more easy. They are more susceptible to stresses and pressures. So what we make is a testable prediction based on this theory, that this material lies very close to the boundary between the regions where two-third plateau can exist or cannot exist. So just by, let us say, applying some pressure or some stress, if possible, I don't know, that experimentalists would know. In principle, you can play with this material under some external conditions which may sort of, even if they slightly tune the value of JB, JCs, it can easily go into the other phase where there is an absence of two-third plateau. Some differences also I would like to sort of highlight, and the differences are, as I said, the theory would of course suggest a very flat plateau. By the way, these are finite temperatures QMC data, so still it is flat, sufficiently flat. But the experiments show a steady rise in the plateau regions where zero plateau should have been, or where one-third plateau is. There is a small but steady rise. And pretty much with the same slope, as you can see. And so the point is, there is something else. And for instance, there is also no clear sign of saturation even at 70 Tesla, whereas theory would basically saturate at that point. So it's clear that there is a scope for exploring other interactions in this system, which are definitely there, but somehow subdominant. I'm saying subdominant because the gross features are all easily or clearly explained by the minimal model that we have studied. But the most natural candidate, for example, would be to incorporate Zalosinski-Moria interaction and see how, if these differences could be reconciled, or what other interaction would be required to reconcile these differences. With that, I end my talk. Let me just summarize. So this compound is a spin-half quantum paramagnet with the Kagome-Honeycomb structure. Just to remember that it's a honeycomb, but with Kagome superlattice formed on it. It realizes hexamer singlet ground state. We have established that clearly. And occurrence of one-third plateau is in fact a strong evidence of that, because otherwise it would not arise if this basic model is applicable. The material lies very close to the boundary of the two-third plateau region. Thus, it can undergo a quantum phase transition to a phase without the two-third plateau under some experimentally created conditions, which only experimentalists would be able to better appreciate. But I'm just making a possible suggestion. Thank you very much. And I stop here.
Let's thank Brijesh.
Yes, Carlo. Yes.
I have two questions. One question is that how do you differentiate between the dimer phase and the hexagonal phase? Do you have an order parameter? Like the hexagonal phase, I think, doesn't break the C6 symmetry, the dimer does. Did you look at any order parameter? Second, if you look at a single hexagon,
but one thing I would like to say, the model, there is no spontaneous, okay, except for, So let me make a point very clear. The model, there is no spontaneously created hexamer or dimer. This is already there. The ABCs are all different in a manner that there is a hexagon, that's all. There is 6 spins coming together and coupled weakly, or a pair of spins forming together and coupled weakly. So the hexagon is given.
Yeah, I mean, it's difficult for me.
What I'm saying is, I see the question he's saying. Suppose I had, think about the simplest and the most important model of spontaneous dimerization in frustrated magnets. Of course, this is not frustrated, but I'm just, by way of example, I'm putting it. If you consider this model with J1, J2 coupling, the nearest, this famous Majumdar-Ghosh model, then it forms spontaneously two dimer states, either this kind or this kind. Now here the model itself did not prefer the one type of dimers or the other. It had complete symmetry as far as every bond is concerned. But the system spontaneously chose to go into either one type of dimers or the other. Here I'm saying the hexamer in some sense is the entity that is given to you by this small distortion. Okay? And the question is, and the dimer is also given to you in principle if you think theoretically. Now the question is, which of these so-called given phases, the possibility that is given to you by this general enough picture of this material, which phase does it belong to? Does it belong to the dimer picture or does it belong to the hexamer picture?
I mean, my question is that how do you differentiate between these two? What is the difference between hexamer?
Well, there are 6 spins versus 2 spins.
I mean, okay, so let me put the question differently. If you have a single hexagon and you introduce a dimerization on the bonds, is there any level crossing as you go for the 3 dimers to the perfect hexagon? If there is no level crossing, then you can't, I don't see how you differentiate between the two phases.
That is a very good question. In fact, I'll go back to this phase diagram just for, so indeed, when we do triplon analysis, which means we by hand pick up either the hexamer or dimer as the reference, then we get this blue region, the region between the blue boundaries. But for instance, in QMC, it was not easy to distinguish because as he pointed out, and as I have said earlier, apart from this central line, everywhere the dimerization is also part of the hexamer. So it's so when I say hexagonal state or hexamer state, it means the 6 spins coming together and forming a spin, whether given to be dimerized internally or not. So that clear distinction is not there. That is why this dashed line is also in some sense representing the dimer tendencies which are present in the system. But the recent ED and an alternate QMC by these other people, I have to look at the details of this paper. But they actually, so I must be honest and say that numerics in our case was not very clearly being able to distinguish between what I'm calling as dimer phase versus hexamer phase. But the more recent work, and which is complementary to ours, which means they have used and they have sort of characterized this is the model problem in a slightly different manner, they do agree that there is indeed a dimer-like phase. But yes, dimerized hexamer is also a dimer problem. But the point is whether the dimer strengths are strong enough to think of the coupling between B and C is different, or to think of it as one entity, that is important. One more technical remark, because Carlo is curious about it. Let me go back to this energy level diagram I showed you when you asked me the question about triplons. So if I just go by this simplistic triplon analysis picture, I have the lowest singlet and then, sorry, what is it? Yeah, I have the lowest singlet, and then I have a unique triplet. I could just form the theory in this subspace. We do that, and we actually don't get that interface region where the dimer phase is approached neatly. Only when we include this other triplets, then only we approach the dimer corners correctly. So you are absolutely right. The corners are in, being approached from the center adiabatic.
Brijesh, we have two more questions from the audience up there. Frederick.
Yes, in fact, I think it's related to what Carlo was asking.
Hi, Frederick.
Hi, hello, Brijesh. If you go back to your phase diagram, the phase diagram.
Yes.
So at the center, you have nail order. Imagine you go along a curve that goes around the nail order phase.
Yeah, like this.
Do you have any phase transition in the ground state? Do you have any gap closing, level crossing? Or
no, gap closing would never. No. Okay, good. So there is no gap closing.
Brijesh, let me finish. I mean, I'm not talking about singlet triplet gap. I'm talking about singlets. Do you have a change? Do you have a crossing between two singlet states, or do you have just a smooth evolution of the wave function with no singlet, with no gap closing?
So I'm saying at the level that we have calculated, these lines are from level crossing indeed, these blue dashed lines.
So you have a level crossing between
level crossing, yes. This blue dashed line is obtained by level crossing, which means comparing the energies of the dimer phase versus the hexamer phase.
So this means that you have first order transitions.
That's there. Right. That's right.
That's what you're saying. You have a first order transition, and this phase goes to okay.
That's right.
Okay.
Yeah.
Okay.
But this is seen in the spectrum. If you look at the spectrum on a big enough system, you should see a singlet crossing another singlet, and if they cross, they have to have different symmetries. So I think this would have implications for the spectrum.
Mm-hmm. No, I cannot give you better answer than that right now.
Okay. We should move on. We should move on to Yogesh quickly.
Yeah, thanks. Brijesh, so are you aware of any neutron scattering work which estimates J's for this system?
No, I don't think so. There is a neutron scattering work.
Okay, not yet. And so an experimentalist's question. So the dimer phase and the hexamer phase are both gapped, right?
Yes, yes.
So experimentally, how do I distinguish between the two?
This is the question which Carlo was asking me.
Right.
Yeah.
Okay.
Because the saturation,
I think
everything should be the same. So
see here, the point is very clear. In this case, the hexamer versus dimer distinction is not that of a spontaneous type, that you can think of dimer-dimer correlation or some structure factor. And so here it's given, of course, at the level of in my mind as a theoretical model for this system, or even the distortion is leading to that physics, the physics of hexamer or dimer possibility. What exact experiment, what structure factor features would actually be able to distinguish between these two needs to be calculated. Okay. I have not done, we have not done, but this recent paper has, as I said, done some large scale ED and also different characterization using QMC. They have some structure factor calculations. But even there, I couldn't point out a particular feature to distinguish between the two.
All right.
Okay, I'll have a look. Thank you.
I think we should move on.
Thank you.
I just have one tiny question. From the dimer phase to the nail order phase, Triplon analysis finds a first order transition.
Yes.
Does QMC also do that?
Sorry, say it again.
From the dimer to the nail order.
No, that is, I think, continuous. I mean, Megdeepa can recall. This red line is what? When you do dimer calculation, there also the gap closes continuously now. Yeah. And wait a second, the first order transition that I mentioned, or that Frederick was alluding to, is between the dimer and the hexamer phase.
And QMC also confirms that it's a first order transition. Sorry, second order transition.
Not very clearly.
Okay.
All right, I think with that we are really late here, but it was very interesting discussion. Thank you very much.
Thank you, everyone.
Thanks, Brijesh. Thanks, Arno.